This is the most basic experiment. If A equals 2, we would use a two-sample t-test to see if changing the factor level significantly changes the response. For this section, we will assume that A greater than 2. By assuming this, we will fit an ANOVA model. Notice here that we assume that the errors are independent and identically distributed normal with mean 0 and variance sigma square. In the next lecture, we will talk about how to check these assumptions. We could also write this as a regression model. We normally would only do this if we are interested in predicting the response from the model. We would use an ANOVA model when we are interested in seeing what factors significantly affect the response. We use least squares to estimate the parameters, which in this case are the TOS and the overall mean. You should notice that what is in the parentheses is equivalent to the errors. This is why the least squares procedure is sometimes referred to as minimizing the sum of the squared errors. These parameters that we find from least squares are not the true parameters. These are only estimates. This is because we are dealing with sample data. So if we ran the experiment again tomorrow, you would get different estimates for the parameters. Notice that after making the assumption, the estimate for the overall mean is the overall average, and that the estimate for the effect for level I is the difference between the average of the response at that level and the overall mean. Since we assume that the errors are normally distributed, it can be shown that the average at level I is a random variable that also follows a normal distribution with the mean and variance shown. Now, if the SUBI are constants and the sum of the SUBI is 0, then any linear combinations of the averages also follows a normal distribution with given mean and variance. You should also notice that when the number of replicates for each level is equal, that n will replace NSUBI in the variance. Here is an example of the one-factor case, where A equals 4 and n equals 5, so the number of runs in the design is 20. Here is the response data. Notice that we have already found the averages per level. Let's find the mean and variance for the difference between power levels 160 and 220. Here is the calculation for the mean difference. Here is the variance calculation. The problem now is that we don't know the variance, so we will need to estimate it. To do this, we need to find some of the squared errors. This should look familiar. This is similar to L from an earlier slide, except now we will use the estimates and we want to find this quantity. You should be able to see that if we had A equals 2, that this is just the numerator of the pooled variance estimate that would be used if we assume equal variances. Notice that the SSE is not unbiased for sigma square. We need to adjust it so that it is. We will do this by dividing it by NA, which is actually an N or A N1. We call this the mean square error within variance or error variance. Here are the calculations for our power example. The upper confidence bound is quite conservative for sample size determination. It will give you the best peace of mind. Notice here that we used alpha instead of alpha/2. This is because the bound is one-sided, so we want all of the probability on one side. Note here that I am assuming that the critical value is leaving probability to the left. Here is the calculation. Now that we have estimated sigma square, we should decide what hypothesis we will test. Here we would like to test to see if the means are equal. Note that rejecting this hypothesis only tells us that at least one pair of means is different from each other. It does not tell us which ones or how many. How should we approach this test? We could do multiple t-tests, but that will cause the alpha to increase quickly. What we need to do is figure out a way to test this with a single test. We will use ANOVA to accomplish this. Here we will use an f-test because we know the distribution of a function of the ratios of the estimates of the between versus overall variances. Here is the general setup for our one-way ANOVA experiment. The hypothesis that we saw earlier is based on the means model. We use the above hypotheses if we want to use the effects model. You should be able to convince yourself that they are equivalent. These are based on the assumptions that we saw earlier on the errors. In order to create this test, we need to find the between variation, which in this case is a pooled estimate of the differences between the mean at level I and the overall average. In order for this test to work, the estimate needs to be unbiased for sigma square. To make sure that this test is valid, we will use the expected mean squares. The way this works is as follows. Find the EMS for the estimated between variance given that the null is true. Find the other MS term that has the same variance. The test statistic is the ratio of the two. In this case, given that under the null the TAs are 0, the EMS for treatment is sigma square. You should notice that the EMS for error is also sigma square, so build the test statistic in this manner. If the null is true, then MS for treatment equals MS for error, so the ratio is 1. So since we are only concerned about the MS for treatment being larger, we use a one-sided test for greater than. We get the chi-square pieces since we assume normality. We also know that the ratio of two independent chi-squares over their df follows an F distribution. So we need the independence assumption there. We also need the equal variance assumption there because otherwise the two sigma squares would be different and not cancel out. The SS are additive. The df are also additive. Here is the ANOVA table. We can use the rejection region method to decide whether or not to reject based on a given alpha level. We could also use a p-value. The p-value is the most overused quantity in statistics. Recall that no matter what Minitab prints out, the p-value is not 0. My stats major do not know what a p-value is. Make sure that you do. Now let's get back to our example. Here is a graphical summary of the data. You can see from this that we have a good chance of rejecting the null hypothesis. Here is the ANOVA output. Based on a reasonable level of alpha, we should reject the null. Here is another example that I will give you SAS code for. Here is the data. Here is the code to get the data into SAS, create the boxplot, and run the ANOVA. Again, based on a reasonable alpha, we would reject the null. One of the most common questions in experimental design is, how many samples or replicates do we need? Unfortunately, there's no single universal answer. Sample size depends on several practical and statistical considerations. We need to think about the type of experiment, how much variability we expect, available time and budget, and most importantly, how sensitive we want the experiment to be. When we talk about sensitivity, we mean the ability of the experiment to detect a real difference when one actually exists. For example, if two formulations differ only slightly, we need enough observations to reliably detect that small difference. If we only care about very large differences, fewer samples may be acceptable. Another way to think about this is through the concept of the minimum detectable difference. Sensitivity is closely tied to variability. If the process is highly variable, we usually need more replicates to separate signal from noise. That leads to the last point on the slide. Increasing replication generally improves sensitivity. Why? Because more replicates reduce the uncertainty in our estimates. The standard error decreases as sample size increases, making it easier to detect smaller differences in means. Of course, there's always a trade-off. More replication improves statistical power, but it also increases cost, time, and resource usage. So in practice, sample size determination is really about balancing statistical confidence with operational constraints. Later, we'll connect this idea to power analysis and see how alpha level, variability, effect size, and replication all work together in determining sample size. We usually decide on an alpha level, but many times we don't think about beta. Most people use sample size to control beta. We need to first get an idea of what sigma square should be. If we have info from a previous experiment, we should use it to get the upper bound. This will most likely give us a conservative value for n, but better safe than sorry. If the null is false, then the expected mean square for treatment is no longer just sigma square. Therefore, the F distribution is not correct. So we will use a non-central F distribution with an extra parameter that we call the non-centrality parameter. The power of a test is 1 beta. This means that it is the probability that W2E reject the null when it is in fact false. We want the power to be as large as possible. Notice here that if the null is true, then the non-centrality parameter is 0, and the distribution of the test statistic is a central F. Only n, nu2, and delta are dependent on n. We can use this iterative process and continue to increase n until we find the desired target power value. Let's go back to the power example. Here are the calculations for n equals 2. Notice that this gives us a power that if far from 90. Normally you would need to continue to increase n until you got to 90. I have written a function in R to do this for you. It is in my courses and called sample size fixed. The function is sample.delta. Here is how you use it. Open R, download it from www.r-project.org. Copy the function into R now at the command prompt type sample.delta, alpha equals 0.01, sigma equals 25, delta equals 75, a equals 4, endpoint equals 10. Delta is capital Delta, and endpoint tells R at what n you wish the function to stop at. Here are the results that you should get from typing in the command on the previous slide. Note here that we get a power equals 0.90 at n equals 6. You can find this under stat/power and sample size/one-way ANOVA. Notice that we get the same answers. You can also specify a minimum increase in the standard deviation instead of a minimum mean difference. If we divide by sigma, then we can get this increase as a percentage. We can find delta here and proceed iteratively as we did in the previous case. Let's go back to the power example and use a minimum increase in the standard deviation of 20%. Here are the calcs for n equals 2. Again, I have created a function in R. This is also in the file sample size fixed, and the function is called sample.percent. Based on the previous function, you should be able to figure out how to use it. Here we find n equals 13. Next time we will talk about random effects.